Open Systems Interconnection, or OSI Layer 1, also known as the physical layer, is the focus of this presentation. We will explore its role in signal transmission, encoding, and the physical media it utilizes. Let's begin our journey into the foundational layer of network communications. Let's explore the key concepts of the physical layer. The physical layer is the lowest layer in the OSI model. It handles raw bit transmission, defines electrical, mechanical, and procedural interfaces, converts data into signals for transmission, and is a hardware-focused layer. You can see its position with respect to other layers on the right side. Let's explore the core functions of the physical layer. First, signal transmission. This involves converting digital data, that is zeros and ones, into electrical, light, or radio signals for transmission across physical media. The physical layer uses electrical signals with copper cables, light signals with fiber optic cables, and radio signals for wireless connections. Next, physical connectivity. This defines the mechanical and electrical specifications for the physical connection between devices, including cable types and connectors, pin layouts and functions, and physical network topologies. Then data encoding. This determines how bits are represented as signals on the transmission medium, using methods like Manchester encoding, NRZ, which stands for non-return to zero, and AMI, which stands for alternate mark inversion. Finally, transmission synchronization. This ensures the sender and receiver are synchronized for proper data interpretation, covering bit synchronization, clock recovery, and transmission rate management. Here is an explanation of how digital data is converted to physical signals. This involves signal types such as electrical signals, commonly used with copper cables, light signals, which are used with fiber optic cables, and radio signals, essential for wireless transmission. Binary data is represented as voltage, light, or radio wave patterns. These signals are transmitted through various media like copper, fiber, and air. Each medium uses a different type of signal to transmit data. Let's examine how data encoding techniques are used. Data encoding is how bits are represented as physical signals. Some common encoding methods include non-return to zero, Manchester encoding, alternate mark inversion, 4B/5B encoding, and 8B/10B encoding. The diagram shows examples of NRZ, Manchester, and AMI encoding, along with a clock signal for synchronization. Let's discuss the physical pathways for data transmission. There are three main types of media: copper, fiber optic, and wireless. Copper media includes twisted pair cables, either unshielded or shielded, and coaxial cables. These use electrical signals and are common in local area networks and telephone networks. The advantages of copper media are its low cost and ease of installation, but it is susceptible to electromagnetic interference, or EMI, and has distance limitations. Fiber optic media includes single-mode and multi-mode fibers. It uses light signals and is used in high-speed networks and long-distance communications. Fiber optic media offers high bandwidth, is immune to electromagnetic interference, and can transmit over long distances, but it is more expensive and difficult to splice. Wireless media uses radio waves like Wi-Fi and Bluetooth, microwaves, and infrared. It uses electromagnetic waves and requires no physical medium. Wireless media provides mobility and eliminates the need for cabling, but it raises security concerns and is susceptible to interference. Let's define bandwidth and throughput, which are key performance metrics at the physical layer. Bandwidth is the maximum theoretical data transfer rate of a medium, measured in bits per second or BPS. Throughput is the actual amount of data successfully transferred over a medium. It is typically lower than bandwidth due to overhead and interference. Factors affecting performance include signal-to-noise ratio, transmission medium quality, distance limitations, and interference sources. The diagram illustrates the difference between bandwidth and throughput, showing how throughput is affected by overhead. Now let's examine physical network topologies, which define the physical arrangement of network devices and cables. The bus topology connects all devices to a single cable, requires terminators at both ends, and uses a simple linear arrangement. The star topology connects all devices to a central hub or switch, with the hub or switch managing all communications. It is the most common topology in modern networks. The ring topology connects each device to exactly two other devices, with data traveling in one direction around the ring and token passing controlling network access. In summary, the physical layer is the foundation of all network communications. It is responsible for converting data into signals for transmission, defines electrical, mechanical, and procedural interfaces, uses various encoding techniques to represent binary data, supports different transmission media such as copper, fiber, and wireless, implements physical network topologies, and addresses bandwidth, throughput, and signal integrity. Up next is OSI Layer 2, the data link layer, where we'll discover how networks handle addressing, framing, and error detection at the link level. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.